Okay, let's look at the concept of electric, eventually electric potential, but we're going to do that by way of introducing the potential energy in an electric field, um, which we will get to by way of looking at how a charge moves in an electric field. So let's set up for ourselves the simplest possible case for this, and that would be a uniform electric field. Okay? Now, a uniform electric field in a particular direction. Let's see if we have. I'm trying to correlate this with the textbook. They don't actually use this, but we'll go ahead and do it. Let's just call this the x direction. Okay, y. And this electric field here could have been created by a parallel plate capacitor with equal and opposite charges on either side. And what we want to do is insert into this electric field here a positive charge Q. Now when we do that, that electric charge is going to experience an electric force. And so the force on charge Q will be equal to Q times E. Of course, we remember the electric field from a parallel plate capacitor, uniform electric field, has a specific um, value. It's just equal to sigma over epsilon, where sigma can be thought of as the charge per unit area on the plate of the parallel plate capacitor. So this we have a plus Q over here, a minus Q over here, and so that would be the electric field that this little blue charge Q is in. And so the electric force experienced by the blue charge Q would just be Q times E, or we could write it as Q over A epsilon naught, like that, in the x hat direction, because the force that the charge is going to experience will be in the same direction as the electric field. Positive charge. Okay, great. That's all well and good. But now what we want to do is let's take a electric take this electric field, same electric charge in the field, and move the charge. All right. So if we want to move the charge, we're going to have to apply a force, because the electric force that the charge is experiencing will want to cause the charge to move anyway. And if we want the charge to move differently, then we're going to have to apply a force. So let's just say that we have this charge, let's say over here. Whoops, I missed the plus sign. Not a big deal. Okay, and we want to move this charge this way. Okay, so if we're going to do that, then what we have to do is apply force, F applied, that balances out the electric force that this charge is experiencing. It's experiencing a force Fe to the right. We have to apply the force F applied to the left. And the applied force the force we apply is going to be equal and opposite to the electric force. Okay, so if the electric force is in the x-hat direction, the applied force will be in the negative x-hat direction. The work that we're going to do then will very simply be computed by the integral from the first position that we have to the second position. And we can call these particular points, so your book actually just says P1 and P2. The work is we integrate from P1 to P2 the applied force dotted into the path length, okay, that we move. So the path length would be the distance that we actually move the charge. If we move it from here, P1, to here, P2, then this is our path length, and a differential path length would be like that. So in moving it, the differential path length is actually equal to minus dx x hat, because it's in the negative x direction. And so the applied force being also in the negative x direction and equal in magnitude to the electric force. In this case of a charged capacitor, I would just get Q times E dotted into dl. Now the applied force is negative Q times E, and so the work done by the applied force, the work done by F applied, and that's the work that I'm calculating here, would be minus Q integral from P1 to P2 of E dot dl. Okay, so far so good. In fact, you could write this as the integral, well, it's the integral of F applied, but, oh no, okay, so I've got that already. Okay, good. Minus Q times E dot dl. Now, you can also think about this in a different way. The applied force does work. The electric force also does work. And so the work of the electric force will be the same, integral from P1 to P2, of the electric force dotted into dl. Of course, the electric force is opposite, directed opposite to the charge. And so the electric force being oh, okay, hang on. Let me back up just a minute. Hold that thought just one second. We'll come back to that in just a minute. But let's go back over here to the dl, okay, because I have a dot dl, okay? I haven't resolved that yet. So the applied force is in fact minus Q dot E. Now the E here, let me make it a little more general. The E is in the x direction. The electric field is in the positive x direction, and x hat. But dotted into dl, dl is in the negative x direction, and it's L like that. So this actually ends up being Q x hat dot x hat gives 1, but that negative sign, there's two negative signs there, and so they cancel out. And so what I end up is E dx. Okay? This actually ends up being a positive quantity. And the reason is because we have to do a positive amount of work in order to move the charge against the electric field. Okay? The dl is negative because we're moving along the negative x direction, whereas the electric field is operating in the opposite direction. So in moving the charge from P1 to P2 against the electric field, I have to do, or the applied force has to do, a positive amount of work. Okay? So now go back over to where we were calculating the work done by the electric force. So here we have the electric force, which is Q times EX x hat. Okay, the electric force is in the positive x direction. Dotted into dl, but the dl is minus dx x hat. So the work done by the electric force actually ends up being minus, we can bring the Q out. The E, the reason I'm leaving the E in here, for the field that we've got, it does not depend on X, and so that actually would come out of the electric field, but I don't want to go there just yet. In a steady electric field, that also could come out of the integral. But I'm going to leave it in there for now just because I want to keep this a little more general. Okay? And there's a dot here, x hat dot x hat gives 1, and so we end up with a minus dx. And so what we see here is the work done by the electric force is equal to the negative of the work done by the applied force. Well, that makes sense because the applied force and the electric force are in different directions. But they end up being opposite amount of work. So a negative amount of work. If a charge moves against an electric field, the electric force does negative work. Okay? And again, if the applied force does positive work. Now you might think, okay, this sounds a little familiar to something that we saw in first semester physics. and that is if I have a ball, okay, in a gravitational field, and I want to raise the ball, lift the ball up from P1 to P2, okay? Now remember, um, on this ball we have two forces. We have the applied force, which we're using to raise the ball up, but we also have the force of gravity, right? And remember when we calculated the work done by the applied force, okay? Well, that's just going to be the applied force times the distance, delta H, let's say, that we move this thing. Of course, I could have written that as an integral. I could have written that as integral of applied force dot dl. I'm kind of simplifying it here because the gravitational force is in fact constant. So the work done by gravity would be the gravitational force, and so here I am going to be a little more dy. Let's call it dy, okay? And just to be really proper and everything, shoot, if I could grab all that, I'll go ahead and write the applied force in terms of the integral too. Integral of the applied force dotted into dy. Okay, and yeah, we won't take that out yet. We'll just leave it like that for now. Okay, so the gravitational force is downward minus mg in the y hat direction. We're moving it upwards, so dy vector is actually dy y hat. So the work done by gravity ends up being minus integral, there's an integral here, mg dy. And since the mg comes out, it's the integral of mg dy. And so this is from y initial to y final, p1 to p2, which, oops, I missed the minus sign, which is minus mg delta y. This is the work done by the force of gravity. So since delta y is positive here, you go up. The work done by the force of gravity is negative as you move the ball up, right? Same thing here. Since the applied force is negative or equal and opposite to the force of gravity, the applied force would then actually be equal to minus mg y hat, or plus mg y hat. So if I look at that, the applied force mg y hat dotted into y hat, or y dy hat, y hat dy. And the mg comes out, integral of y hat dot y hat is 1, and I get the integral of dy, which is just mg delta y. So the same kind of thing is happening with this gravitational example that happens with the electric field. As I move the ball up, the work done by the applied force is positive. I do a positive amount of work because I'm exerting an applied force upward and the ball is moving upward, displacing upward. So the work done by the applied force would be positive. Since the force applied is equal to the force of gravity, mg, that amount of work then is just mg times delta y. And the work done by gravity is equal and opposite that. The work done by gravity is minus mg delta y, because the mg is down, the delta y is up. Okay, and it's the exact same thing with the electric force. The electric force is doing a negative amount of work, just like gravity is doing a negative amount of work. The applied force is moving against the electric field, is doing positive amount of work. Okay, so hopefully that analogy kind of makes a little bit of sense. Remember, though, that when we did this with gravity, we noted that this work done by gravity ends up being independent of path. Since I have the delta y, it only depends on the endpoints, y initial and y final. And it doesn't, we don't care if I take the ball and move it straight up or if I take the ball and move it around like this, if I end up in the same spot, I get the same amount of work. It's the same amount of work because the direction of gravity and the direction of the displacement are the only things that um, influence it. And so, this is what we call a conservative force. A conservative force is one where the amount of work it takes to move an object does not depend on the path that's taken. And so, in a conservative force, like gravity, the work done by gravity, we said, ends up being the negative of the potential energy. It was advantageous for us to define this quantity, potential energy. Um, Literally is the negative of the amount of work done by the conservative force. Okay? Well, maybe you see the analogy that we're coming up with here. The work done by the electric force is also equal to the negative of what we're going to call the electric potential energy. And so, this is how we define potential energy. Potential energy is the negative of the work done by the electric force, which actually happens to be the positive of the work done by the applied force. Okay? In this little example that we've given here. So let's take another case in point. Let's do a point charge. Okay? So if we have a point charge, remember that we know we'll have a plus Q here, a big Q. Okay? And we know what the electric field from that looks like. It's radially outward in all directions, right? Something like this. And we know the electric field from a point charge is equal to KQ over R squared, and it's in the R hat direction. All right, so now let's put a little test charge, plus Q, in that electric field. And if we move it from a point 1 to point 2 in that electric field, how much work do we do? So the work done by an applied force in moving it from P1 to P2 is going to be the same applied force dotted into D. I'm going to say R here because, well, I'll just say DL. Why not? DL, whatever path length I choose to move it. So now let's be specific, and let's say what we're going to do is we're going to move this plus Q from this starting position R1, okay, like that, to this ending position here, R2. All right, so the direction of motion of the charge is actually from here, R1, to here. That's going to be a little path length in here is the differential path length, as we're going from R1 to R2. And I can even call that a vector, okay? Applied force dotted into DL. Well, again, we're going to have to actually exert force in order to move that, because the electric field itself, the electric force, wants to move that charge outward, right? The electric field is outward. We place a test charge in that electric field, it's going to experience a positive force trying to move it outward. And so the applied force will be equal and opposite to that charge, to that force, in order to get it to move, which will look like this then. Q times E, okay, and that's negative F applied dot DL. Now the DL I can be a little more specific about too, because in this case DL is equal to minus, actually, because it's pointing inward toward the origin, so dr in the minus r hat direction. So what I'm going to get there, the integral from R1 to R2 of minus QE dot minus r hat dr. And then let's be specific about what E is. Okay, E is the field from the point charge. And so R1, R2 minus Q. Now for the E, I'm going to put in K big Q over R squared, and it's in the plus R hat direction. And I'm dotting that into minus R hat dr. So what we see is that the minus signs are going to cancel out again. I get R1 to R2. Surely there's things I can take out of this integral. In fact, all of these things that I've just written could be taken out of the integral, right? KQ, Q. In fact, let me go ahead and do that. All of those are constant, so they move outside the integral. And then I have R hat dot R hat, which is 1, and I have a dr over R squared. So now I have to keep that inside the integral, right? KQ Q, and integrating from R1 to R2 dr over R squared. That integral is something that I can do, though. Again, this is the work by the applied force. And what I'm going to end up getting is you integrate dr over R squared. That gives you a minus 1 over R. So it's minus KQQ 1 over R from R1 to R2. And so notice too that this has now taken two vector quantities, the f and the dl, and it's created a scalar quantity. So the work is simply a scalar function, minus KQQ 1 over R2 minus 1 over R1. Or you could just write it as KQQ 1 over R1 minus 1 over R2. Take the negative sign out. Like that. Right. And then if I wanted to know the work done by the electric force, it's just going to be, maybe you can guess this, the negative of that. Notice that there's no direction associated with that. Again, this is just a scalar quantity. So KQQ 1 over R2 minus 1 over R1. All right, that's what you get with a point charge. And so that's pretty interesting. There's another implication of this, of calculating the work like this. Let me just kind of put this in a sidebar here. This is a pretty important implication, but let's spell it out. If I go on a closed path, let's say that I want to calculate the work done by the applied force from R1 to R1, and it doesn't matter what path I take, okay? R1 on P, let's say. Let's say that R1 starts here and the path goes way around here like this and comes back eventually. Okay, that's path P. Doesn't matter how it does it. But the point of all this is, if I do f applied dot dl, what I'm going to end up with is the same thing, KQQ, 1 over R1 minus 1 over R1. Well, guess what that gives you? 0. And so drawing out from this, and by the way, this, if this is, if these integration limits are the same, then you could write this as the closed path integral of f applied dot dl. But let's make it even more explicit. Q E dot dl. Okay? And you say, well, there's a negative sign in there. Okay, fine, there's a negative sign in there. But the point is that this equals 0. And so if I divide that negative q out, I can come up with this general principle, that the closed path integral of the electric field dotted into the path is equal to 0. Okay? Now this is going to become a little more familiar. We're going to use this one in a bit. This is actually one of what's called Maxwell's equations. We just developed the integral form of it, but it tells us a lot about how electric fields work and everything. Okay, so all that to say, we've calculated the work done by the applied force using the same thing that we came up with up here. Remember that the work done by the applied force ended up equal to the change in potential energy. So here's what we can say. The change in potential energy of a point charge moving from P1 to P2 will be equal to K, Q, Q, 1 over R1 minus 1 over R2, like that. And so that's a general expression for the potential energy between 2 point charges. If one of them is located at R1, the other one's located at R2, you can do it like that. In general, though, when you do this kind of thing, you're thinking more about the potential energy of a collection of charges, or maybe even just one charge. But the potential energy would say, okay, how much work would it take to bring another charge and bring it close to this other charge, to bring it close to this charge that you're looking at? And so in that case, you would be integrating from some reference location to the point where you want to bring the charge, okay? And it would be K times the charge that you're bringing divided by or times the fixed charge divided by R squared dr. And that's going to give you this value here, KQQ times 1 over R minus 1 over the reference location. And so generally it's not a bad idea to set the reference location for these problems to go off to infinity if you can, which means that the potential energy at the reference location is set to 0. And if you can do that, then you can say the potential energy at location R from a single point charge. It's important to note this is a point charge. That potential energy is going to be K Q Q over R, and then minus this reference potential energy, which usually you can set to 0 if you can set a 0 potential energy. So that's the basic gist of how you calculate charges. One more result that I want to point out at the end of section 7.1, they calculate the work required to assemble an arbitrary number of charges. Work required to assemble n charges. And so up here, let's see, if we're doing point charges, this is the work required to assemble 2 point charges, KQQ 1 over R minus 1 over R2. And so what they do is they say, well, if you're going to assemble 3, let's leave this for just a second. What if n is equal to 3? All right, well, the work required to assemble the first 2 would be K, Q1, Q2, 1 over R1 minus 1 over R2. Make sure I wrote that right. Yep. Okay. Now the work required to assemble the between 1 and 3 would be K, Q1, Q3, 1 over R1 minus 1 over R3. But then we also have to calculate the work to do 2 and 3, which would be K2, Q3 times 1 over R2 minus 1 over R3. And so if I want the work to assemble all of those charges, work 1, 2, 3, that's going to be the work for 1 to 2, plus the work from 1 to 3, plus the work from between 2 and 3. In other words, and this also, by the way, would be the potential energy of this system of three charges. The potential energy between charge 1 and 2, 1 and 3, 2 and 3. And so they give you a general map. Maybe you can see where this is going. If I want the work required to assemble n charges, I just do all of these things. 1 to 2, 1 to 3, 1 to 4, dot, 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 1 to n, plus 2 to 1. Now this is where it gets tricky, because notice I don't have a 2 to 1 in here, right? So it's not really 2 to 1. It's 2 to 3, which I haven't accounted for, plus 2 to 4, plus dot, 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 2 to n. And I just want to point out that I don't have the 2 to 1 in there because I've already accounted for that. Plus work from 3 to 4, and here I've missed 3 to 1, plus 3 to 2 because I've already accounted for both of those. Plus the work from 3 to 5, plus dot, 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 3 to n, and you keep going. So they give you a general formula for that, which is the sum, the double sum, from I equals 1 to n and j equals 1 to n of k q1 or qi qj over rij. And then, in fact, let me write that in more general terms. Equals the sum from I equals 1 to n, sum from j equals 1 to n, wij. But that's over counting. And by the way, this in both of these cases, it's for I equals 1. I does not equal to j. But you've overcounted this because you've got duplicates. Every W1, you've got a W2. When you had a W23, you've got a W32 if you do this. So you have to take half of that in order to calculate the work done by a system of charges and or the potential energy of a collection of charges. And that's how you do that. Okay, so that's the theory behind the whole idea of electric potential energy, and next we'll define potential difference.